Good morning, everyone, or good afternoon, depending where you are. I'm happy to welcome you today to the webinar ESWET is doing regarding CCS or CCU. And in there, we will ask the question, can waste to energy become carbon negative? Or can CCS help in general the waste sector to decarbonize? And that's a question which is important, known, given that we have the targets of the Paris Agreement we want to achieve, the carbon neutrality of the continent. And for this, we need to understand how we can remove CO2 because we will probably overshoot the Paris Agreement targets. So my name is Clerens. I'm Secretary General of ESWET, the European Association for Waste to Energy Technology Suppliers. And I'm here as a moderator today, moderating the presentation of the experts, way more expert than me on these topics, which is, I will take it from right to left, Jannicke Bjerkas, who's working at Fortum. Then we have Maria Velkova working at the European Commission, and David Kearns, who's working for the CCS Institute, the Global CCS Institute. And they are expert on their field, and I will introduce them just before the presentation a bit later. So we know that we have the European Green Deal in Europe. We know that we have the carbon neutrality target, and we have seen that waste to energy, which is participating in reducing CO2 emissions and did so quite strongly in the past with the effort sharing directive, is able to contribute and is therefore required to do more and to reduce the CO2 emission from the waste sector. Obviously, this goes first by reusing and recycling. And then if you cannot recycle, then at least we say we should use this residual waste in a way which is providing energy and materials back to the economy. It is known that waste to energy plants clean quite a lot of flue gases, and the question is it possible to clean the flue gases even out of CO2 to make them even CO2 neutral or almost? And this is what we will elaborate today. So we will have today first the presentation a bit about CCS from David. Then we will have a specific case in Norway, which Jannicke will present. And finally, we see how subsidies and sub-support on European level exist with presentation of Maria. So with this, I will go over to the presentation of David, and the other panelists don't need to stay present on the cameras. You may obviously. And David, he's a senior consultant in CCS technology in the Global CCS Institute. And as the lead technical expert in the Institute, David provides guidance to the industries and governments, clients on carbon capture and storage technologies, modeling, engineering, economics, and the strategy of this. So David is really very well into this topic of CCS. And his experience spans 2 decades of oil and gas, electricity generation, petrochemicals, biofuels, engineering design, process engineering, industrial AI, carbon and energy consulting, and sustainable processing. So you see he's got a lot of experience he brings with him, so he can help us all to understand better how CCS is fitting in this. So please, David, then the floor is yours for your presentation, and we will take clarification questions just after his presentation, but any other question regarding the content, the general discussion, we will take afterwards in the Q&A. David, please. Oh no, I forgot. Oh, I apologize. I need first to give you the introduction of what ESWET is and what we see. I almost skipped this whole part, and I probably had Paolo, who organized this, completely sweating. Sorry, Paolo. So let's go to my part first. ESWET is an association of suppliers, I told you. And the suppliers means we have different providers. We have providers of equipment, but also of turnkey plants, and they are all excellent technology providers in their sector. All waste to energy plants in Europe are have either been built by ESWET members or have their components. On the next slide, you see the question of how waste is treated in Europe, because that's the basis where we're in. And this is a statistic taken from Eurostat, where you can clearly see that the green part, which is recycling, is the part which also looks at waste to energy. So the countries which have most recycling are the countries looking most at waste to energy. It's not by chance that they are working hand in hand? It is because after recycling, there's always some residual waste, and the best way to treat this, for these countries at least, is to go to waste to energy for this residual part. On the next slide, you see that this is not a European problem, the waste generation, it's a global issue. The World Bank projected the waste which will grow in the world. They have this report, Water Waste 2.0, and in there, they clearly show that by 2050, the waste volume will not reduce, it will increase. It will increase by around 60%, and this is huge. And if you know that most of the plastics in the ocean is coming from, I don't know, a handful of rivers where the wind blows in plastics and which the plastic then is brought to the ocean, you're asking yourself if this is really the best way, globally speaking, to use landfills, or if you shouldn't make sure that energy should be recovered, the material and the environment be saved from these plastics which are flying around. Today, this means that last year, 70% of waste generated worldwide was dumped. This is enormous, 70%. So this is a huge room for recycling and a lot to do for waste to energy. So the next slide, please, will show you that, as I said, not all waste is recyclable, at least not for eternal times. The reason is very often that the materials are not suitable for the initial purpose anymore, meaning that it has been recycled too often. It is possible that you have polluted waste. Let's say you have a flame retardant in a plastic in a dashboard of a car, and then this flame retardant should maybe not end up in a toy of recycled plastic. Or it is made of such composite products which are not easily recyclable, and or where the effort, the environmental impact to recycle this is higher than the environmental gain to recycle this. And in this case, also it makes more sense to get the energy and the materials out and bring it back to the society. This waste is called residual waste. And so the question is, what happens with this residual waste? For the ones living in Brussels and Belgium, it's the white bag where you put in your residual waste, and the others you obviously use for recycling products. On the next slide, you see that this residual waste is normally, if it's not used for waste to energy, going to landfills. And there it is way more harmful for the environment because it emits methane emissions, greenhouse gas, 84 times more potent than CO2. And there is obviously the risk of groundwater pollution. But this risk of groundwater pollution is normally not in your generation, so you put it somewhere in the earth. The risk will then fall on the next generations when 30, 50, 60, or maybe 100 years later, the protections are getting old and maybe breaking. So it's an easy solution for your own generation, but then you put it on your kids and their grandchildren to take care of this. So this waste which has been landfilled also brings nothing back to the society because the materials are really lost, and even if there's some landfill gas recovery, most of the energy is also lost. So what is the other option? It's obviously to use waste to energy. You'll not be surprised that we advocate this, and we mainly believe it takes out a resource, it takes out the energy, it takes out the material, the raw material. There are a lot of metals in there, also gold and other very valuable materials. And we see more and more that waste to energy plants are linking themselves into the fabric of the cities. You see in some cities they have tennis courts on top. Here they put a ski slope in Denmark, and there is a climbing wall in other parts. So you see that these waste to energy plants not only have a purpose for material and energy, but also have an added value for the local community when they are designed in the adequate way. So the next slide, please. This means that I showed you now what waste to energy, the role of waste to energy we see, but I'm looking forward to your questions on this and remarks. And now it's time for David, which I just already presented, to take over the floor and to share your experiences with us regarding CCS. David, the floor is yours, now for good.
Thank you, Patrick. Hello, everyone. I'm David Kearns. I'm Senior Consultant in CCS Technology at the Global CCS Institute. The Global CCS Institute is an international think tank dedicated to the establishment and growth of CCS as a technology worldwide as a means of dealing with climate change, or one of the parts of the solution to climate change. I've worked with the Institute as their engineer, senior engineer, and so my focus tends to be on the technical and techno-economic aspects of CCS, but inevitably there are policy and other aspects that overlap with what I do. So I'm looking forward to some good questions tonight and a good discussion. Can we go to the next slide, please? A little bit of an overview about CCS and how it works with waste to energy. So first off, what is carbon capture and storage? It's a suite of technologies to separate CO2 from emission streams. So what does that mean? Essentially, most flue gas streams that you'll find around the world, not just in waste to energy, but in power generation, industrial heating, and many other applications, they contain CO2, but it's not pure CO2. It's actually quite dilute in many cases. So in waste to energy, it's in the order of, it varies on fuel composition, but it varies from the order of say around 10 to 15% CO2. And the rest of it is combustion water, nitrogen from the air that was used for combustion, and so on. If we want to be able to take that CO2 out and store it, the first thing we have to do is separate it out and purify it. That's known as carbon capture. And that's the first and sort of, essential first step in the CCS value chain. Once you've got that CO2 out of your flue gas, then you can actually think about where you're going to put it. So generally speaking, there are opportunities to utilize CO2 as a feedstock. And so you'll hear about CCUS sometimes, with the U standing for utilization. But our expectations are, in the long run, there's going to be far more CO2 than there are actual uses out there. And so storage is going to be essential. The predominant storage routes are going to be geological storage, so that is storing the CO2 deep underground. When you look at CCS in bioenergy applications, it's a very special case, because unlike conventional CCS, where you're simply reducing the net emissions from a plant or a process, with bioenergy, because the CO2 is biogenic, meaning that essentially the CO2 was quite recently in history in the atmosphere, if you capture that CO2 and store it, you've had a net reduction of CO2 from the atmosphere. It's an actual negative emission. Sometimes it's called carbon dioxide removal. And of course, this is relevant to waste to energy plants, because a substantial fraction of the fuel composition that's used in waste to energy plants is of biogenic origin. So it's wood, leather, food scraps, and so on. Now, the general rule here is, if you can capture a higher fraction of CO2 from the flue gas than is the fossil fuel fraction of that flue gas, the process becomes carbon negative. So if it's 50% fossil fuel coming into your plant and 50% biomass, if you can capture more than 50%, you've just become carbon negative. So the diagram at the bottom gives you an idea of what's going on. CO2 from the atmosphere gets absorbed when biomass is grown through photosynthesis. And also, one of those key streams is municipal solid waste, which is clearly of interest to the audience here tonight. Some of those get turned directly into biofuels, but many of them get converted to heat and power in waste to energy plants. The idea is that we have a capture plant that sits on the back end of that waste to energy plant. So it takes the flue gas coming off that plant. It uses the application of heat and work, generally, usually in the form of electricity. And it captures a substantial fraction of the CO2 coming off that plant. Now, the precise amount is a question of economics as much as anything else. It will never capture all of it. There's always going to be some leftover CO2 in the residual flue gas. The rule of thumb that's been around for many years is that a figure of 90% of the CO2 is a figure to target. But in recent years, some studies out of the IEA have suggested that you can go to 95% or higher without substantial economic penalties. The reason we don't go to 100% is that it's just a matter of cost. The closer you get to 100% CO2 capture, the higher the costs become. And so there's basically a limit to how far you can go. Next slide, please. So how does capture and storage work? So this diagram on the right here is a fairly typical example of what's known as an absorption or a solvent-based capture process. And that's the dominant technology that's used worldwide for carbon capture. There are other technologies, but they're not especially relevant for waste to energy. They basically consist of two towers or columns. One is known as an absorber. What the absorber's job is to contact that flue gas stream coming in on the left-hand side. It's been cooled in a flue gas cooler. It contacts it with a solvent. So you've basically got flue gas flowing from the bottom of the tower to the top, and you've got solvent flowing from the top to the bottom. And usually there's a packing in there just to give good surface area and good contact between the liquid and the gas. The solvent is specifically chosen to have an affinity for CO2. So usually it chemically bonds with CO2. We call them chemical solvents. Those solvents historically have been amine based. So this technology has been around in the natural gas processing sector since 1930. So aspects of this are quite old. The CO2 transfers out of the flue gas into the solvent, and then the solvent becomes what we call a rich solvent. The solvent then flows out the bottom of the absorber tower, goes through a heat exchanger where it basically exchanges heat with the warm solvent coming out of the stripper. And then it goes into a stripper where it's heated up, and then that helps to break the bonds with the CO2 and release the CO2 as a fairly pure gas. So typically in this kind of process, the CO2 gets purified to well over 99% purity, which is definitely enough for storage applications. There's an ISO standard that has suggested that 95% CO2 purity would be the minimum that people would be expecting. That's not a hard and fast rule. There are other standards and other expectations, but 95% is not a bad way to go. There are other solvents that are used. So the traditional solvent is MEA, monoethanolamine. MEA is very mature and there's no IP. You don't have to pay license to use it, but it does have the downside that it's quite corrosive, and it also suffers from something known as solvent degradation. So you'll see as you go from the absorber to the desorber, you're basically heating up and cooling down repeatedly these solvents, and over time they suffer from thermal degradation. That basically means that the chemical starts to break apart and form byproducts that no longer work as a solvent. And so MEA forms waste in the end that needs to be taken out of the columns and replaced with fresh MEA. And that can actually be a fairly substantial cost if you use MEA as a solvent. And so there's a whole industry out there and a whole R&D effort going into alternative proprietary solvents of various chemistries. One of the main things they're looking for is to reduce that solvent degradation. Another is to reduce the regeneration energy. So that stripper tower on the right, it has a reboiler that puts heat in to heat up the solvent to separate the CO2 back out. That consumes the bulk of the energy of the capture plant. And so people are looking for solvents that can still capture CO2 effectively, but won't require so much heat, basically, to get the CO2 back out. Once the CO2 comes out, on the top right of that diagram, we've got a CO2 stream going off to compression. That CO2 is wet, so it's saturated with water. The solvents that we use generally are aqueous solvents. Now, those of you who have a knowledge of chemistry will know that CO2 and water make carbonic acid very, very acidic and will rapidly corrode metal pipelines that you might put them in. So there's generally a dehydration step in conjunction with compression. So we compress our CO2 up to what's known as dense phase properties generally. That means you go above around 74 bar of pressure. What that does is that converts it into a dense phase. If it's a little warmer than that, we call it supercritical. What that means is that it gets a lot more density, and it means we can fit a lot more CO2 into a given pipeline. Once we've got our dry compressed CO2, it can then go into a pipeline. An alternative route, which we're seeing in Europe now, and you'll certainly be hearing about tonight, is shipping. Now, shipping supercritical CO2 is not quite so well suited. So instead we go for liquid CO2 where it's moderately compressed. It's still dried very effectively, but it's only moderately compressed, and then it's refrigerated, chilled down to very cold temperatures, and that liquefies the CO2 suitable for putting in a ship and taking it to a storage site. Next slide, please. I guess the main point I wanted to get across here with CCS and waste to energy is this idea of negative emissions. And what's really behind the interest in that is the unrelenting arithmetic of net zero. So net zero doesn't mean that we're not going to emit anymore. There's going to be certain industries and certain sectors where emissions are either unavoidable or it is just so expensive to abate them that we really need to find another way. If you look at the chart on the left, this is from the European Commission 2050 Strategic Vision, and it's a projection of what would be required to reach a 1.5 degree scenario by 2050. What you see there is that the bars for all of these different sectors, transport, industry, power, they're all getting smaller as time goes on. But you'll see even on the far right at 2050, when you're at net zero, there are some positive emissions sitting there. You've got emissions from agriculture, you've got emissions from tertiary sectors, from transport, including aviation, which is very hard to decarbonise. And the way that we can offset that and make net zero emissions is we can use negative emissions. And there's basically three main categories that you can do that with. One is to do with growing new plants, so either afforestation or reforestation, so either growing new forests or regrowing old forests. Direct air capture, so that's capturing CO2 directly from the atmosphere, and that is certainly a very sort of vibrant area of R&D and work at the moment. And bioenergy with CCS or BECCS, and that's really where waste to energy fits in. The waste to energy sector is really well placed to take advantage of the opportunities that BECCS offers to help contribute to dealing with our emissions problem, because for just a range of reasons, the technology is obviously available today, not only the waste to energy technology, but the CCS technology. It's commercially available. You can go to a vendor and buy it today. It's not limited by land availability. So growing forests, obviously, you're going to have to grow forests where that land is being used for something else. That can be a challenge. And the biomass supply in municipal solid waste is not only available, but it's continuing to grow. So as Patrick showed you before, the World Bank has projected 60% growth in municipal solid waste to 2050. That is a large and growing source of biomass, and it's already collected, distributed, brought to central points. The hard work of getting the biomass has been done. So it's a really, really promising and really exciting opportunity for the industry to grow. And of course, one other thing that waste to energy offers is that it can help prevent future landfill emissions, as Patrick said. So not only are we getting a reduction of emissions through negative emissions, but we're also preventing future methane emissions as well. So you're getting sort of two fairly substantial emissions reductions. That was it from me, Patrick. So happy to have any clarifying questions now, if that's what we're doing.
That's what we're doing. Thank you, David. Very clear. Okay. Very concise. Thank you for keeping the time. Are there, I'm looking at the chat, I don't see any questions on the chat for clarification. With this then, I would move on to the next panelist, and I would introduce Jannicke. Thank you, David. Talk to you in a moment. So, good morning, Jannicke. Jannicke Bjerkas is Director CCS at Fortum Oslo Varme. And Jannicke is the Director of CO2 Capture and Storage. And she started at the Oslo Varme District Heating in August 2017. And what is very interesting is that Jannicke helped to start up the CCS project in 2014. And you see, so 2014 to 2020, 6 years. So it's something you do in a short time period. This is really well thought through and well organized. So in addition to the current role, we see that Jannicke worked as Director of Human Resources Communication in Fortum Oslo District Heating. She was the Director of Communication and Strategy at the City of Oslo Energy Recovery Agency, and then Chief of Staff of the Waste to Energy Facility in Oslo at Clemensrud. She is also a former officer in the Norwegian Air Force, and this you don't see so often. Very nice. I'm very happy to have you here, and I'm looking forward to your presentation and learning from your experience since several years on getting this project flying. Jannicke, the floor is yours.
Thank you very much, Patrick. Yes, as Patrick said, I'm in charge of the carbon capture project at Fortum Oslo Varme's waste to energy plant in Oslo. Our company has two owners, where Fortum is one of the owners. Fortum is an international energy company focusing on sustainable city solutions and sustainable waste handling and infrastructure. And our other owner is the City of Oslo, with very ambitious climate goals, where this capture project from the largest CO2 emission source in the city is essential to reach the climate goals for 2030. Next slide, please. Our capture project at the waste to energy facility is a part of the Norwegian state's full-scale project for establishing a full value chain of CCS, and it's called Longship, from the old Viking ships. I will come back to our role in that project shortly, but we are one of 2 capture projects, where the other capture project is a cement factory. Both will be transporting CO2 by ship to an intermediate storage place at the western coast of Norway, where the CO2 will be injected into a permanent geological storage about 3,000 meters below the seabed. And the aim of this project is to establish an infrastructure and a storage place for CO2 emissions all over Europe. So our part is to demonstrate that this logistics chain is working and that the capture technology is also working on an industrial emission source. Next slide, please. A little bit more technical about our project. So we have a waste to energy plant, which is actually the largest one in Norway. And we are emitting about 430,000 tons of CO2 every year, and with plans to increase. Our goal is to capture about 90% of the CO2 emission from this plant, which is about 400,000 tons from 2024. So this is something that we have tested and proven, and we know that it's going to work. As Patrick and David has already covered quite nicely, waste to energy plants, the flue gas from waste to energy plants contains about 50% biological CO2. So this means that our industry can be crucial for Europe in their aim to reach the net zero target, because we can capture large amounts of biological CO2. Our waste to energy plant is not situated at port, which means that we have to transport the CO2 from our plant to the port of Oslo. That's a distance of about 10 kilometers. And we are planning to do that with emission-free trucks. We have been investigating a pipeline, but it proves difficult both due to price, but also to regulatory issues going below a large city with a lot of other activities in that hill. So for the first phase, we have decided to go with these trucks. We have also been testing the chosen technology. So we have chosen amine technology, and we have chosen Shell's proprietary technology. This technology has already been proved in Canada on both coal and also on gas power. However, our flue gas is different. So we decided to build a pilot and test the specific technology on our specific flue gas. So we tested for about 9 months with very good results. We have very high capture rates, very low emissions, and a stable operation of the pilot plant. So we are confident that this plant that we're planning to build, the full-scale plant, will work, and it's going to capture large amounts of CO2, and it's going to be safe for the environment. On the lower picture on the right, you can see the colored parts is the planned capture plant. So it's quite large, and I think that's one of the development areas that we need to see on these plants, is to reduce the footprint in order to have them fitting in with the existing industry. Next slide, please. So this slide has been nicely covered by both Patrick and David, so I will go briefly through this. But as mentioned, waste amounts will increase in the future, and we know that waste is a source of large global emissions that we need to address. We have to move away from landfills, and we need more waste to energy in order to handle the residual waste that we cannot recycle. The BECCS potential, or bio-CCS potential, is important, and we will get back to that. And we can also state that if the EU if and when we reach the recycling goals and the goals for reducing landfills in the EU, we lack 40 million tons of waste to energy capacity in order to handle this residual waste. So the potential in the business is large. There's going to be a lot of new plants, and hopefully in the future we can see them built with integrated CO2 capture as part of the flue gas cleaning process. Next slide, please. So a little bit back to Longship and our project. In September, the Norwegian government proposed their decision for the CCS full-scale project, and they have decided to support the full transport and storage chain, and also Norcem's capture plant with full financing. For our capture project, we received conditional support, which means that we have to find additional funding of about 3 billion or 95 million euros. Excuse me, that's the wrong number. Approximately 300 million euros we need to find additional funding for. So we have received about half from the Norwegian government if this is decided in the parliament. And we need to find the additional funding to actually realize our plans. So this is why we have applied for the European Innovation Fund for the rest of the funding. And we are, of course, hoping that we will receive funding in the first call. Our project is mature and it's ready to go. And it's also replicable to similar plants all over Europe. So we believe that this is a good case to take down emissions efficiently. Next slide, please. So I will summarize the main points that I have been already discussing. CCS is a technology that we need in order to reduce emissions fast enough. It's safe, it's proven. We've done it in Norway on gas power for about 25 years, and it's a very effective solution. CCS on waste to energy will contribute to negative emissions and also to reach this net zero target. And another important aspect with waste to energy is that these plants are closely connected to cities and the city's infrastructure and cities' climate goals, which means that by capturing this CO2 from the waste to energy plants, we can contribute to the cities reaching their climate goals. Thank you. Patrick, I think you're muted. I still can't hear you.
I suppose.
Now I hear you.
Yes, so I have to check my headphones. So thank you very much, Jannicke. It was very clear. It shows really the added value that your project has on reducing CO2 emissions, and also, as you said, going negative. So it's a really very interesting and very impactful project. So I'm very happy you presented this. We'll have, I'm having a look if there are some questions, but I don't see any clarification questions for the moment. So we come back to the Q&A to you. Thank you very much, Jannicke.
Thank you.
Let's go to the next speaker. The next speaker will be Maria Velkova. Maria is Policy Officer in DG Climate Action of the European Commission. Her main task revolves around the implementation of the Innovation Fund and the support, which is the support for large-scale demonstration of carbon-reducing technologies, basically, in industry and energy sectors. Maria also follows the EU policy and regulatory work on carbon capture, utilization and storage, and she worked before this in the regulation on greenhouse gas emissions from transport, fuels, and on supporting research and innovation in renewable technologies. And Maria worked for the Commission now since 2008 and has therefore also a great experience on the policy and the work and the efforts done by the Commission to reduce greenhouse gases, which is enormous. So, Maria, thank you for the time. Very happy to give you the floor to walk us through CCS and waste to energy and the Innovation Fund.
Thank you, Patrick. Good morning, everybody. So I'm really actually happy that the presenters before me made my life a bit easier because of this excellent overview of the CCS and waste to energy and the potential. So if I can have the next slide. And this is actually what David explained. So this allows me to explain a bit more maybe on the next slides, which is really excellent. So if you could go on the next slide, please. I will focus actually here on maybe on the specific role of CCUS and how we see it in the vision for a clean planet by 2050, because it is clear indeed that we will need not only CCS, but we will need negative emission technologies. And here what we heard already is that some of those technologies with big potential combine the use of biomass and CCS. And if you actually see on that slide, we have here the different scenarios which we have analyzed. And the previous graph, we actually, the graph we use most of all is in fact corresponding to the 7th bar here, which is 1.5 tech scenario. And please bear in mind that only the 3 last bars bring us to climate neutrality in 2050. So in fact, the first scenarios, we actually don't even look at them any longer. And what is also important to say is that the last 2 bars, where we have actually least emissions, very much rely on consumer participation, very strong reduction of emissions through consumer behavior. So to be honest, we really rely mostly on the 1.5 tech scenario, where all technologies, all our low carbon technologies we see have a role, including CCS. And the amount of CO2 which needs to be permanently stored or is amounting to more than 600 million tons a year, and half of it is actually through permanent storage, this like kind of brown part here, but we also see a lot of potential for synthetic fuels, the gray part here, or synthetic materials which offer a more long-term storage. So yes, the opportunity is there, it is big, but we need to get to there. So if you could go to the next slide. It recaps actually what we have been doing for CCUS over more than 10 years. We have, like, first and foremost, of course, it's really important that we provide regulatory certainty in a long-term perspective. And I believe this is what the Commission has been doing throughout this decade, that we are very serious about reducing emissions, and now the long-term perspective is really firm. We have to be climate neutral by 2050. We are actually attempting to go faster in reduction of emissions. You know that now the targets for 2030 are increased. So we want to reduce emissions by 55%, which is going to be challenging. But what is there for CCS? For CCS, we have the CCS directive, and even if it is not applied yet, because we don't have actually CCS projects commercial in the EU, it is a very, very important directive, because it ensures that any CO2 storage that is done in Europe and EEA countries actually as well, of course Norway is covered, is done safely for the environment and human health. And this is incredibly important, because if there is ever a problem with a big CO2 leakage, the public will most probably not allow further CCS. But we have the certainty that the CCS directive is there, and applying it will ensure that. The EU ETS is our main directive, which incentivizes low carbon technologies. And it is true that it hasn't been able to incentivize CCS yet. But the reason for that is that the CO2 price has been low, because there were other solutions which industries preferred to use than CCS. They could reduce emissions with energy efficiency measures, which were very cheap. In fact, they allowed them to save funds. The economic crisis which we had actually in 2008 to 10 to 12 also had a role, because economic production reduced. But in the future, the allowances which will be on the market will be less and less, and industries will have to resort to more expensive technologies, including CCS. Waste to energy plants for the moment are not covered under the EU ETS, mostly in most countries, and also the same is for biogenic CO2. So what we have in mind is, well, you know that there will be, of course, a revision of the EU ETS in order to achieve the higher target for 2030, and that is one possibility to include other sectors in the EU ETS. We still don't know what will be the outcome of this revision, but what we are already working on is a scheme to develop an EU certification scheme for carbon removals. And this scheme, which we plan to have in place by 2023, is going to be there for any carbon removals that are not covered by legislation in practice. So if waste to energy or BECCS stays outside the EU ETS, it can be enabled to support it through this certification system. And what we have, of course, what will continue there is support to research through Horizon Europe, support to infrastructure through Connecting Europe facility. For the moment, only CO2 transport is supported. In the future, maybe CO2 storage as well, but we don't know yet. And of course, the Innovation Fund, which is the program actually I know most about, and I would like to spend a little bit time on it. So if you could move to the next slide. I know that you know really a lot about the Innovation Fund because we have been doing quite a lot of publicity. And so this is a program which we say will have 10 billion, but maybe it will have more because it depends on the carbon price. So that calculation is done with a 20 euro carbon price in mind. And we will have annual calls for large scale, both for large scale and small scale projects. The sectors which are eligible for funding are basically all energy intensive industries, which are covered by the EU ETS, renewable energy, energy storage, and carbon capture, utilization and storage are also eligible. Waste to energy plus CCS is fully eligible. For the moment, our interpretation of the directive is that waste to energy combined with only CCU, utilization, is not eligible. That is like kind of interpretation of the legal basis. So if you can move to the next slide. What is important here is that there are a few messages I want to pass. Why Innovation Fund is different. Innovation Fund is different because we almost don't have a cap on the amount of funding we can give to one project. So the funding is capped by the 60% of the funding gap. So we cannot fund more than 60% of the funding gap. So projects normally have to find additional funding from public resources. So they need to believe in their own technology and invest in the future of this technology. What is differentiating the innovation from other programs also is that we can support single applicants. We don't need consortium or like participation from more member states. However, of course, scalability of the technologies are important, and scalability may be achieved better if there is participation from more countries, but that is not really a requirement. So if you could go to the next slide, because I know I don't have so much time. Jannicke already mentioned we were actually quite successful with the first call for large-scale proposals. We got more than 300 proposals, which request 20 times more than what we have, or even 22, close to 22, meaning that there is really high competition. Of course, all these proposals are under evaluation now. We don't know the quality yet of the proposals, but we are sure that they are really very big number of very good proposals. And this is what we see by, well, looking at the proposals at the moment only internally. So if you could go to the next slide. There is a nice map of like, which shows actually another outcome of this competition is actually we have proposals from across Europe. Of course, some countries where research is stronger, where industry is stronger, have more applications than others. We also have applications from all possible sectors, from all categories, and we have CCS 14 proposals, which have identified themselves as CCS proposals, but in fact, CCUS is present in many other proposals. Actually, more than 30 additional proposals will have a strong component of CCU or CCS. And these are spread throughout the different sectors like steel, chemicals, and also waste to energy, which is falling in a category other. So it's not under the category CCS. So a lot of proposals overall from CCUS sector. If you could go to the next slide. I just want to, well, advertise our future call for small-scale projects. Maybe it's less relevant for the audience today, but just to say that on 1st of December, we're announcing the small-scale call, and that is for projects which have capital expenditure below 7.5 million euro. I won't spend more time on it in the interest of time. So I think I have one more slide just to show the calendar of the first two calls. The first call, the large-scale call, which I talked about mostly, is still at the beginning. Actually, the grants we can award only at the end of 2021. It's really quite a long process, but given the amount of interest and which we were expecting this big interest, we have proposed a two-stage call. We actually now starting to consider whether in the future to change the submission procedure to move to one-stage call in order to be able to give the grants faster, but that is to come. So more or less for both calls, the grants will be awarded at the end of 2021. At the same time, there will be a next call for large-scale projects, which will be announced around middle of 2021. So if you're not successful, if projects are not successful in the first call, there will be annual possibilities to apply for funding. So this is from me. And I'm of course ready to answer any questions.
Thank you, Maria. Thank you very much. Also very interesting, very clear. We see that there's quite some support, being on policy, being on evolution in the ETS, or financially with all the different funds you mentioned in the obvious innovation fund, but also the others like Connecting Your Facility and so on. With this, I would invite the other two presenters back, and I would then open up the panel discussion and Q&A. Basically, the aim here now is to take your questions, to make a real panel discussion. So I would ask the three panelists to leave their microphone open. I would ask you to behave as is a normal panel discussion, so you can interrupt people, you can add to people, obviously everything in a polite way, I hope, and so that we have a real discussion ongoing, and we are not very sterile in a webinar asking, oh, please, what do you think, So a real discussion, you can interrupt and speak whenever you feel that you have something to add. And I will not necessarily give the questions to a specific person. I would ask you to reply if you feel that the question is touching you. So we had some questions already. First of all, I will take the ones in the order as they came. There were questions regarding the cost, obviously. And this is, I suppose, was to Jannicke and to David maybe, about the cost of installing this. So the first questions were, what is the CAPEX of a full-scale plant to be installed? Can it be said that if you want to remove, I don't know, 1,000 tons, you need X million euros? Is there a relation? And then also maybe if it's easier to retrofit or easier to foresee it from the original design. So this cost issue, what does it mean, CCS, in the installations? I don't know. Please just jump and take the floor whenever you feel ready.
Okay, I guess I can start with the specific project that we have developed. The CAPEX cost for our project is estimated to approximately 430 million euros. We have some specific cost adders to our project, and one of them is obviously the transport and the fact that we need an intermediate storage at Clerens because we're not situated at port. The other, it's a cost adder, but it's also a resource perspective to this, and it's the fact that we need to reutilize the heat from the capture process to bring back basically the energy that we are giving to the capture process back to utilize it into the district heating system. And this is valuable energy that we manage to reuse by investing in a heat pump. So this is an extra CAPEX cost, but it's also enabling the utilization of this heat energy from the capture process. So that's a good combination with district heating system.
Yeah, I would add to that. I was going to say that that's a very good sort of specific example of some of the ways that costs come out in CCS. The way that costs have worked in CCS projects around the world thus far have shown that it's very dependent on economies of scale. So large projects tend to have lower costs per ton of CO2 captured than smaller projects. And so that will be one thing that if CCS becomes more widely deployed, it would incentivize the development of new waste to energy plants to be on a bigger scale, because that will be favorable for the economics. The transport aspect is certainly important as well, as Jannicke mentioned, even for pipelines. Pipelines in more densely populated parts of the world like Europe are obviously more of a challenge because you have to try and run them, not necessarily in a straight line like you can in less populated parts of the world. And another aspect that doesn't always get a lot of attention is that the costs of compression and or refrigeration need to be taken into account as well. It's not just the capture plant. I think historically people have given almost all of their attention to the capture plant because that's the big impressive thing that people can see. But some of the less glamorous parts can contribute to cost as well. And so that may have an influence on siting of facilities. So you may choose to move a facility or build a facility rather that is close to a port or closer to a storage site and bring the waste to it rather than trying to run the CO2 down long lines. It's a complex thing to try and work through all these issues and come up with the best plan. But what we have seen on the other side of it is that capture technology is improving and experience is improving. So we now have some fairly significant scale capture plants in the world. If we take the example from power generation, for example, the world's first large-scale power generation capture plant was in Canada. The costs of that we at the Institute have estimated to be about $100 a ton for capture. But just a few years later, the Petronova plant in the US, so really it was only I think 3 years later that it was commissioned, was about a third less per ton. And it was similar scale. In fact, it was slightly larger. So there was some benefits from economies of scale, but some of it was just learnings. So there's always, you always see this technology curve of the first of a kind is always the most expensive because everyone's learning the expensive lessons and making all their mistakes. And then those lessons get passed on to everybody else and you find that the second is cheaper, the third is cheaper again. And so it's one of the most exciting things about the project that we're discussing today is that that's going to put some real world experience at scale in waste to energy. And those lessons that are learned will then be applicable and usable for future projects and help bring the cost down for those as well.
So it's basically the economics to make sure is the reason that it's not more installed. It's the cost issue mainly and how to cover this. It's not a technical issue, you said.
The technology works. There's no problem with the. I mean, the engineering is doable. It's a question of economics and making trying to do it at least reasonable cost. Okay, so this was one of the questions I wanted to cover. Then the other question I will try to cover myself is should only be the biological fraction be considered as BECCS, or should also the fossil fraction be considered as BECCS? I think it's quite straightforward. Only the biological fraction can be considered as bioenergy carbon capture and storage because the rest is fossil energy based. So this is quite clear. Is there also, Jannicke, again, first questions. Did you calculate this on how much this would add to the ton of waste treated? I mean, there's a certain cost to treat a ton of waste by using CCS on top of this. Did you break it down to this level?
Yes, we did. And the capture cost of CO2 is approximately adding about approximately doubling the price if you're putting everything on the gate fee. So this, yeah.
And which would this mean in Norwegian kroner or in money, in euro?
So this is of course because this is sensitive to competition, so it's very
okay.
yeah.
Okay.
But say approximately 50 to 70 euros per ton.
Okay. Per ton of waste treated. Thank you. Great. And then a question with the storage. The risks for deep sea underground storage, have there any been identified? If yes, which ones and how are they dealt with? Do you have any information on this you can share? I know we're not experts on storage, but maybe.
Yes, so the Institute obviously has expertise in storage as well. I guess a few aspects that people might want to know first off. The first is that the storage is at significant depth. So we are not doing shallow depth injection of CO2. Typically it's in the order of 2 kilometers or more. I think Jannicke said it was 3 kilometers in the Longship example. So that's the first aspect. It's not close to the surface. The second is there's a significant amount of work that goes into characterizing a storage resource. So what that means is work that's very similar to the work that's done in oil and gas exploration of really understanding the geology that's below the surface. What you're looking for is you're looking for a geology where there is a porous rock, which has essentially got lots of holes in it that can accommodate CO2 that you inject into it. But over the top of that is you have an impervious rock that won't allow the CO2 to come back to the surface, because CO2 is lighter than water. It's buoyant, it will try to float up. And so that's what we're looking for. We're looking for formations that have those properties. They're very similar properties to what you see for natural gas formations. So when you seek natural gas, that's the kind of formations you often find them in. And so really we've got sort of two aspects to this in terms of safety. One is depth, the other is finding very significant thicknesses of impervious rock that will make sure that it stays put. The other thing to bear in mind is that the CO2 is not very mobile. Once you put it in place and once it gets into the rock, a lot of the CO2 dissolves into the water, and a little bit like CO2 dissolving into a fizzy drink. It's not really got an incentive to bubble back out. And in the longer term, you will see in many places, if the rock chemistry is right, you'll see mineralization. So the CO2 will slowly turn into carbonates, so solids. And so the longer term, essentially the risks diminish over time as the CO2 turns to solid.
Okay, thank you. Jannicke, you want to add something specifically for this project, or has everything been covered by David?
Well, I think David covered it very, very nicely. For this specific project, I know that they have a layer of sandstone, which is the porous stone that David was referring to, and with a layer of shale on top of it. So it's very stable. And as I also mentioned, this is something that Equinor has been doing for 25 years, removing CO2 from the gas stream. So okay. Yeah, we have quite some experience on that.
Thanks.
Patrick, if I may
yes,
add, just like to repeat a little bit what I said already, at least in Europe, there won't be any storage sites selected which have risks, which show where the CO2 actually may leak. So at least in Europe, but given that we're talking here about a global problem, we perhaps need to work a bit even more globally to ensure that the same really rigorous appraisal is done on storage sites across the globe. And of course, there is an ISO standard for that, there is international work, but in many countries, and in the countries where this is done, generally, indeed, there is like really thorough appraisal work, which is preceding the permitting of storage sites.
And for the storage, Maya, since you have the floor, you mentioned different funding, also the Innovation Fund and others. Which one would you see would be the most suitable in your experience to really push for waste to energy put down on a waste to energy plant? CCS on a waste to energy plant. Would it be the Innovation Fund, or are there other funds which are more suitable, or a combination? Can you combine the different funds to make something like this happen?
Yes, I mean, we can indeed, innovation funding can be combined with other resources, and it is actually necessary, as we see here, the projects which come to us are large-scale demo projects, first of a kind, which are much more expensive than the commercial plants. So that's why there is a financial gap. There's a good reason that public intervenes, and we can actually fund only up to 60%. So the rest of the money should come from somewhere else. And I think here it is really the role of the member states to support this type of projects, but also to support the development of the transport and storage infrastructure, because it is an infrastructure. Innovation Fund is mostly for innovative technologies. There isn't so much actually innovation in the infrastructure per se. I'm not saying that it's not entirely not present. No, I mean, in storage sites, there are new monitoring techniques, for example, new drilling techniques. There's a lot of innovation there. Therefore, we are completely open. We can support, but given the competition, Innovation Fund alone cannot deliver the transport and storage infrastructure that is needed across Europe. And that's why I mentioned Connecting Europe facility. For me, that is indeed the program which can support the infrastructure together again with the member states.
Thank you very much. A lot of questions come. Yes, please, Jannicke.
Could I just also add to what Maria is saying in the demonstration effect? It's clear that these first projects, as goes for ours as well, will be costly, but it's important to focus on the demonstration effect and also the learning curve that we will see from these first projects to the next. And for our case, as I mentioned, these cost adders with both the heat pump and the transport is also important demonstration measures for the other projects in Europe that are not situated at port and will need to find solutions to transport the CO2 and also to reutilize the heat. So I'm quite certain that we will see substantial cost reductions to the next projects. Great.
That's encouraging. Thank you, Jannicke. There are a lot of questions about the technical part, so maybe I would take some of them. The flue gas composition after the separation, how is it? How does it look? If you can go very short on this. I don't know, Jannicke or David, can you, specifically from the West Energy?
So I can give you the fairly standard target that has been designed into most CCS plants has been targeting 90% capture fraction. So 90% of the CO2 in the flue gas is separated. So essentially the residual CO2 is 10% of what was there to begin with. Now that is a design decision that is not inherent to CCS. You can certainly go higher. What we find is that as the capture fractions go to 91, 92, 93%, the marginal costs of capturing that last ton, they go up. And there's a point where, the marginal cost reaches a point where it's just not sensible to continue capturing anymore. From a technical perspective, you could certainly go, to very high capture fractions. Okay. It's just a point of, is it sensible to do it?
That's for CCS, but what are the other composition, the parts in the flue gases in the waste energy plant once you took away the CO2? What is still there in these flue gases is the question.
Well, they're very selective solvents that are used. So they are selective for CO2, well, for acid gases basically, and in the flue gases you see from waste to energy, that's basically CO2. So the residue is nitrogen, a little bit of residual oxygen, water, and I guess if there's any, other trace gases, they're most likely to remain in the flue gas as well. So you do still have to have your gas treatment. That doesn't go away. You need to treat for the standard pollutants that you'd have to treat for. It really is essentially just what you start with, remove the CO2, and then it doesn't really remove anything else.
And it's also clear that the flue gas from waste to energy, it's much cleaner than, for example, flue gas from coal power. So that's something that we learned from our pilot is, as David mentioned, very high capture rates. We demonstrated up to 99%, but it's a cost question. So we are aiming towards 95% capture rates.
Okay. Did you have to change the flue gas properties were before they go into the capture plant? Did you have to filter more? Did you have to do anything else with these flue gases to get them ready to be captured, or was the normal flue gas stream enough?
Well, the normal flue gas cleaning is enough. It's quite clean, the flue gas that comes out of the cleaning process. There is a pre-scrubber before entering the capture absorber tower, but that's basically it. And then we have an additional cleaning step, of course, of the flue gas after the absorption tower to make sure that there are no emissions
Of amines
going out with the flue gas.
Okay, so really with the waste to energy carbon capture and storage projects, the flue gases are even cleaner than otherwise. Good.
And it's very suitable for CCS.
That's very nice. There's a question on, let me see, from the energy part, can you say how much energy is used and consumed by the capture plant from the one which is generated? I mean, you recover it then also with the heat pumps and so on, so that you bring the energy back to district heating. Do you have any precise numbers or ideas how much energy of which is normally generated would be consumed for the capture?
I don't have the exact numbers, but we are delivering steam to the capture process and then reclaiming low temperature heat of about 40 degrees. So I believe we are reclaiming about the same amount of energy, although it's more low temperature energy, but it's about the same amount as we're using for the capture process is reclaimed after the stripper. That's
encouraging. Thank you very much. Generally, the projects like this, what are the hampering points? Is it the permits? Is it the funding? Is it the acceptance? What did you experience would be the main points that hampered or took longer? The hurdles you had to overcome?
Well, to start with the more project specifics, I would say that the combination of the state criteria with the industrial process was quite challenging. We have been discussing costs several times. I would actually emphasize that we should focus not only on the cost, but we should focus on the value of this climate measure, because that's what it is. It's a climate measure. It's something that we need to do to reach the net zero target, and we need to develop this technology. So we need to focus on the value, but we also need to find financing for these projects. And that's why we need such as innovation fund, and that's why we also need to get these incentives in place that Maria is mentioning. Yeah, when it comes to bio CCS or BECCS. So that's very good news that we will see some of that in place by 2023, because I think that will be a contributor to lift these projects in the waste to energy industry.
Can I ask Maria? Sorry.
Sure. Yeah? Go ahead.
So Maria, there's a question specifically for you. So we see CCU that it's mentioned as being complementary to CCS, and it's also part of the graphic, let's say for fuel and so on. But it is claimed that the regulatory framework only really supports CCS. And as an example, the ETS, MRR or taxonomy is supporting CCS, not CCU as such. Why is that reluctant? What would you say? Is it reluctant knowing that we will also need CCU?
Well, yes, maybe my message was not entirely clear. Indeed, in our modeling, we do consider CCU and the possible role that CCU can play. But CCU is a term which is like quite large because it can concern many different products which have a different greenhouse gas emission impact. Unlike with CCS, where it is clear, I mean, you capture 90% of the emissions, you know what energy you put in there to capture, you can really calculate the emissions that are avoided. You can calculate also in CCU projects, I mean, by using life cycle assessment, and actually for Innovation Fund, we have developed a methodology to calculate greenhouse gas emission avoidance, which is applicable to any project, but that is done project by project. You cannot say in advance CCU will avoid 90% of emissions. We just don't know because it's project specific. And this is why actually our regulation takes CCS as mitigation technology and is incentivized under the ETS, because rules are easy to create for CCS. For CCU, that is not the case, and it's also we have to consider these are more innovative technologies, so they're newer to the market. We have less understanding about them. And with CCS, the directive is, for example, from 2009. So we are considering CCU. We have been studying, we continue studying them, and slowly we are integrating them into the legislation. Like, for example, for CCU fuels, now, like there is a delegated act which will come with a specific methodology to calculate their emission avoidance. And once this is possible, some of those fuels, which are really good, then they can be supported by member states and count towards reaching the targets. And also with what I mentioned through the carbon removal certification, this will work also project by project. And this will allow, again, to support specific CCU projects, which are really good for the environment. So that's why there's quite a big differentiation in our treatment of CCS and CCU.
But you're working on it to have CCU also. That's good. A general question, which maybe is for all three panelists. The question is, if you look at waste to energy, and David briefly touched upon it, there's no need to cut trees down or to transport wood pellets around the oceans if you use it on waste to energy, because this biomass is residue after it had a purpose, a useful activity. So do you think that therefore there should be a differentiation about BECCS, bioenergy CCS on waste to energy, which should maybe be preferred, compared to bioenergy on wood, which is still sustainable regarding the Renewable Energy Directive, but which would still have to be cut specifically in order to make bioenergy? Do you think it's worth it to differentiate it, or should all BECCS be treated the same?
Look, I tend to lean towards, trying not to favour one or the other. What we're really interested in here is CO2 and where it ends up. Having said that, obviously there are some impacts involved in growing biomass, and there's land use change, emissions impacts, and so on, which we don't have to worry about for waste to energy. Of course, in waste to energy, those impacts have really occurred elsewhere in the production of whatever products were originally before they ended up in the waste stream. So I don't personally. I don't think you need to differentiate. I just think you need to make sure that every bit of CO2 in the life cycle is accounted for, and then everything can be on a tons of CO2 basis.
Any remarks? Yes, please.
Yeah, if I could just add one thing, I agree with David, but I think it's also important to recognize that for waste to energy, the main purpose is to treat the residual waste that we have no other solutions for. It's not the production of energy, because that's a byproduct, and it's the sustainable use of that energy, but that's not the main purpose. And that was actually hard to categorize in Innovation Fund, because we are not possible to exchange with renewable energy. It's not the energy production that is the main purpose. It's the treatment of the waste.
So yeah. Some recommendations for the future of the Innovation Fund. Maria, please, if you want to add to this.
Well, yes, I think also, I mean, we don't we always say we are technology neutral. We try not to give priorities. And we try to have as limited regulation as necessary. So hopefully, because as Jannicke says, waste treatment is necessary, this biogenic CO2 will be there and can be captured. Normally, the cost should work better for this type of plants than for plants where you actually have to incur specifically costs to grow the biomass. And of course, we are very insistent on the sustainability of biomass, and that will only be reinforced in the future, so that this biomass actually doesn't harm other parts of our environment. That is also very important. and that is going to add actually further burden to those plants. So
I think it's important to remember too that this is not necessarily going to be a competition between the two. The world is going to need both BECCS, conventional BECCS and waste to energy. We have some enormous hills to climb over the next few decades. We're going to have to throw everything we can at this problem. So every sector, I think, needs to put its best foot forward and contribute where it can.
A question again about the economics. So in Norway, waste to energy is covered by the EU ETS. Is this correct, Jannicke?
No, it's not. We are actually not covered by the ETS. The government is considering a specific carbon tax for the waste to energy industry. But as for now, we are not covered with the ETS.
Was this the main driver for you to run this project? And would Fortum consider to do this also maybe in other parts where there would be no carbon tax or no ETS coverage? How much did it play a role?
I would say it didn't actually play a role because we still don't have that carbon tax. It's still under consideration. So I think the main driver for both Fortum and well, if we start with Fortum, the vision is for a cleaner world. And Fortum is working towards city solutions, sustainable city solutions, sustainable waste treatment. So this is basically a perfect fit with the vision and the strategy, and the desire to be a part of the development and the solution, and to be able to utilize that learning to other projects in Fortum. For the city of Oslo, it's obviously the climate focus and the desire to reduce these large emission points in the city.
Then we have some technical questions. The first question would be, did you identify a minimum size of a waste to energy plant where it would make sense? Or did you not look at these numbers?
Well, I can talk about this from a more general perspective. So there has been, I guess, a development or a recognition that there is a very long tail of smaller emission sources around the world that are going to need CCS. So this is not just something that's going to run on, facilities that produce millions of tons of CO2 a year, power stations and things like that. We are going to need smaller solutions. If you look at the work by Aker Solutions and so on in modularization of capture technologies, that's one approach that's being taken. You are working against economics. So I mentioned earlier on that economies of scale play a very significant role in the costs of CCS per ton. You can minimize the effect of that, but you can't entirely eliminate it. So one of the things that we are seeing to deal with that problem is the emergence of hubs. And so rather than having individual facilities, what we're doing is we're building shared infrastructure for many facilities to all feed into. That makes sense because, of course,
for the transport.
That's for the transport. Also, depending on the location, for compression as well. Depending on the volumes. Unfortunately, with capture, of course, you really do have to do that at the source level. You can't really aggregate flue gases to any great extent unless they're right next to each other. And so that's why I was saying that there's probably going to be an incentive going forward for waste to energy plants to get bigger if they're designed with CCS in mind right from the start. Having said all of that, there is certainly a push by technology providers to try and make the economics more attractive on smaller scales. I would say that I don't believe we're likely to see below about 100,000 tons a year. That's longer term. I think below that, it's just going to be very, very expensive and very hard to overcome. That's just an estimate. That's not a hard number. Because it just comes down to the unrelenting economics of it, that the costs just get very, very high per ton when you're at very, very small scale. Now,
so
having said that,
100,000 tons of CO2 per year is for you a limit, which is.
I think that longer term that will be a limit. I mean, it's way beyond the limit now. I mean, the idea of trying to capture those levels and do it at a reasonable cost today would be extremely difficult. I mean, if Jannicke is talking about the scale of 400,000 tons a year, which, I mean, at today's example is probably, that's really getting down there. I think to go lower, we're going to need those learnings. So we're going to need the first of kind experience. We're going to need the learning curve. We're going to need modularization, better technology, but eventually you start bumping up against physics and chemistry and economics, and you will reach a limit. Precisely where that is, I don't know, but I would be very surprised if even by 2050, if people are capturing sources under 100,000 in this way. They'll find alternatives. They will find other ways to abate CO2.
Okay. Jannicke, do you have something to add to the question of the size for your plant?
Yeah, I agree with David that I think modular solutions will be a key development for these smaller emission points. But we also see, especially in Norway, but also in Scandinavia, that cities are pushing their plants because they recognize these emission points as important to reduce for the city's climate goals. So we see that waste to energy plants in Norway, in smaller cities, smaller plants, are really looking seriously into this technology and trying to find ways to capture the CO2. So this will be an important development, I think, from the first largest projects.
Great, thank you very much. There are questions now. We are almost done. We have 10 minutes left, so I will go to the last questions. Questions are regarding the EU certification scheme you mentioned before, Maria. Some of them, I will read them, but I suppose it will already require the outcome, knowledge of the outcome, which is difficult to do in forehand. But the question is to follow. Will there be an economic incentive linked to this EU certification? Will this economic incentive, if there would be one, be linked to the price of the EU ETS, so of the ton of the ETS, or be independent? And in general, how would it practically be implemented? These are a bit the questions. If there's incentives, if yes, if there would be the cost of the ton of CO2, and how to implement this certificate.
Yes, there will be. The idea is that there will be an economic incentive. One of the possibilities is to link it with the EU ETS, but this is not yet on the table, as we just started with a study how to design the whole scheme. So this part of the options, how to incentivize, will come only at the very end, because first we need the methodology, we need to see which technology options, because we're actually talking about nature-based solutions also, not only technology-based solutions. So the idea is that it's an over-encompassing scheme. And what I want to actually maybe promote a little bit, although without the information yet, is that early next year there will be a public consultation linked to this study. So if you're interested in that, do follow what is coming out from our side on this, because input from stakeholders, of course, will be considered. And especially it's very important now at the beginning at the onset of this of the design of this scheme. So nothing is decided, but we realize that we cannot create this certification system without an incentive behind. It won't work.
Yes, so there will be an estimation. The next questions would be maybe a bit more specific. I mean, we know that waste to energy now is starting to look at this. Do you have any specific tools to share the knowledge? Is there anything in place that you in your project asked to make some knowledge sharing related to the funding, or how is it done for you, Jannicke?
Well, we have been focusing all the time on sharing our learning. So we have been hosting several seminars and webinars, both from the pilot plant operation, but also from the process, the project process. This is also actually something that the Norwegian state has been very specific on, that for them to be co-funding this, they also expect us to share learnings and to help developing the technology and the development in the waste to energy sector. So we have been working quite actively on that, both in Norway and also in Scandinavia and Europe, to share our experiences, our learnings, and to encourage this development in the sector. And we will continue to do this. Yeah.
That's good.
If I may add on this point, because it's actually also at the heart of the innovation sharing. And it is something which at the moment is not, it's not forgotten, but it's not in the high, well, it's not, we're not talking about it too much because it's too early. I mean, knowledge sharing can happen once projects start, but we actually already planning the knowledge sharing, and we because it is so important. We will be giving money to only a selected number of projects, and we hear that actually costs will reduce only with the second, third commercialization of these technologies, but they will reduce if the knowledge is spread and it's shared to the extent possible. Of course, it's a fine balance, because we have commercial sensitivity. We have to reward the innovative efforts that these projects have done, so we cannot like force them to share all their knowledge. And it's like what we're working on now, also behind the scene a little bit, is like the design of the knowledge sharing system of the Innovation Fund. We need also to have a sufficient number of projects so knowledge can be shared between projects, because it's not sufficient that just they are single projects and we force them to share knowledge, but with whom? So anyway, we're working on that, and there will be more coming next year. We are planning a knowledge sharing event at our previous program, NER 300, where actually we will showcase a little bit in the wind energy sector how this is done, but we will also present what we plan for the Innovation Fund, and we will seek input from stakeholders, how they best see this knowledge sharing system working for, like, indeed speeding the commercialization of technologies, reducing costs.
Great. I will ask you at the end, all three of you, a last sentence, so maybe start thinking. We still have 4 minutes. Last sentence, one sentence about this topic, what you think the people should take with them and keep in mind on this topic. But in the meantime, we heard the fact that in Europe we have the EU ETS or the effort sharing. We heard that Norway was thinking or is thinking about the carbon tax. We see that there's a push in mainly Europe to reduce CO2 emissions, mainly also in other parts. But we are driving this and want to be the first carbon neutral continent. How can we make sure that the others are following, that the others are using this technology? Is this something which must come through political tools, like encouraging them to join a kind of ETS? Is it through helping them to put down the technology, and therefore they will have, and they will see that there are possibilities to reduce emissions and they're more likely to engage this chicken egg discussion? So how do you see this happening?
Well, I think first off, it's important to remember that unlike many other markets, if you don't have supportive policy, you're just not going to see CO2 emissions coming down. You know, it's very difficult to compete with the ability to freely emit CO2, and so that's why any jurisdiction that has that obviously is going to see better results than one that doesn't. But we are seeing a plurality of different approaches. So if you look in the United States, for example, they're using tax offsets. So their 45Q scheme, so they're using carrots rather than sticks to try and push this technology, and they are seeing some success and certainly a lot of interest from industry there. I think that the supportive policy and the leadership of countries, and the global sort of agreement under the Paris Agreement obviously has set the tone and direction. I think the cooperation is going to need to become far more intricate and far more low level. So we're going to need to see, as we've just discussed, the sharing of knowledge. We're going to sometimes have to expect people to go maybe a little bit against their normal competitive instincts, which is not always easy for people in business to do. But yeah, I think the supportive policy is absolutely crucial and essential. Engineers like me love to build stuff, but there has to be an incentive to provide the money to make it possible.
Okay.
So yes.
Thank you. The other two, you have any thoughts on this last question which I just asked? How to get it around?
Right. Well, I could follow. As David says, the incentives and the regulations are important, and it's good news to hear that the EU is working on it and that we will see this coming the next few years. I also would like to challenge the business to recognize that this is something that we need to do. It's something that's coming. It's an area where waste to energy can contribute to important climate emissions reductions in Europe. So this is a responsibility that we have to help developing this technology, to work with also the capture technology suppliers to find good specific solutions for the waste to energy sectors. And as I mentioned, maybe it's possible to integrate this as part of the flue gas cleaning, which could contribute to cost cuts. So I think the waste to energy sector has a certain responsibility to keep developing the business and to keep looking at this area to reduce emissions from the waste handling.
Maria, you want to add to this?
Well, I have to agree with what we heard, and the EU is actually working, you know, both within the EU. We have put the climate action really in the heart of every EU policy, but we're working very much globally as well. Of course, globally, you know, it's difficult. We need to persuade others. The others have to decide to follow or take the lead, even better. But we see really positive developments around the globe, and we are overall optimistic, but emissions are reducing too slow, that we cannot forget. And there is, of course, a question of international competition for our industries. And that's why we are starting also the work on a carbon border adjustment tax, because we can't just be pushing ourselves without without this additional incentive for others to follow. So we're trying everything that is possible. But of course, the environment is a public good, and emitting CO2, as David says, unless it's regulated, unless it's incentivized the removal of CO2, it will not happen.
Okay, so we come now to the end of this webinar. We're 1 minute over time. Maybe if you have one last sentence for everyone. David, can I ask you to start? One last sentence what the people should take away.
The waste to energy sector's got a real opportunity here. In the sense that it's one of the few carbon dioxide removal opportunities that we have. And I really think the industry needs to grab it with both hands. It's going to be here for the long run, even beyond 2050.
Thank you. Jannicke, please.
Oh, that was such a good sentence from David, though. So I agree. Yeah, it's an opportunity and it's a responsibility that we really should embrace.
Great. Maria.
Well, absolutely, and I hope that in the audience there are a lot of companies, they are getting ready their projects, and we are really looking forward to very mature and projects with significant emission avoidance from the waste to energy sector.
Great. Thank you to all three of you. We had roughly 200 participants today who were interested in joining over the time. And I think it's a very interesting topic. We will hear more of this. It will come a lot because we need to reduce this. And I really appreciated the time and the expertise you put at the disposal of all of us. And I wish you all a very nice weekend. And for you, David, your weekend started already. For us, we still have to work half a day. But thank you very much. Have all a nice weekend and see you in future. Thank you.
Thank you. Bye-bye.
Thank you. Bye-bye.
Bye.